Hi, just going to record acid-base balance part 1. Even though I did do this in class on Thursday, and we got all the way through it, I'm just going to record it for anybody who wasn't able to attend class. So this is going to be the initial discussion of acid-base balance, the very first disease in this series of lectures, or first lecture in this series. So acid-base balance pretty much is the control of the hydrogen ion, its production and its elimination to keep the pH or the acid level of the body in a pretty narrow range. Hydrogen ion is actually the cause of a lot of the acid in the body, and so it has the narrowest range of normal in homeostasis, and so it is subject to the tightest control mechanisms of almost all the electrolytes or chemical substances. The body, again, really keeps this hydrogen ion level in a very tight, narrow range. So acid-base balance is talking about the homeostasis or maintenance of the hydrogen ion concentration in the body fluids. Even slight changes in the hydrogen ion concentration can cause extreme changes in cellular reactions, particularly enzymes in any kind of a protein. So for example, if the acid-base balance is out of balance, the acidic nature or base alkalotic nature of the fluid can change in the shape and reduce the function of hormones and enzymes in the body, can also cause changes in other electrolytes that are in the body, and those in themselves, when we change those levels, we might cause problems with fluid electrolyte balance. Or we could change the excitability of membranes, making such structures or tissues like heart, nerves, muscles, and GI tract more or less active than normal, depending on if it's more acidic or more alkalotic. And also, that in itself will decrease the effectiveness of many of the drugs that we give to people. So again, very important to keep the acid-base balance in a normal range in the body. So let's first talk about what we are going to be measuring when we try to determine if the acid-base balance is in the norm. We generally talk in terms of the pH, which is a measure of the body fluid's free hydrogen ion level, which I designate as an H with a positive mark there because it's a cation. So free hydrogen ions are usually in a pretty low number, and we don't measure them. My cuckoo clock, sorry, I'm going to wait till it's done. It's late at night, lots of people. Anyway, I can't measure those by checking the blood and counting them. It's a very complicated formula that's used to calculate how many hydrogen ions that are present. And so what we do is we take the inverse log of the number of hydrogen ions, and the end result is a pH. So in other words, a pH is a negative algorithm, or the inverse of the hydrogen ion concentration, again using logarithms and a lot of really annoyingly complicated math. So since it's a negative algorithm, the inverse of pH is the hydrogen ion concentration, meaning that the lower the pH number, the higher the number of hydrogen ions are present. So if we change 1 unit of pH, there's a tenfold change in the free hydrogen ion. So if we move from a pH of 7.4 to 7.3, drop it, it's going to increase the hydrogen ions and in fact increase it quite a bit. So that is why the body pretty much keeps that pH in a fairly tight range. When the pH is less than 7, we say the solution is acidic or has more hydrogen ion. If it is greater than 7, we say the solution is alkaline or has less hydrogen ion. In the body, plasma, interstitial fluids, wherever, the range that the body likes is slightly basic. It's a pH range of 7.35 to 7.45. When it's below 7.35, it's acidosis, a state of acidosis, which is, again, a high hydrogen ion. As the pH goes down, the hydrogen ion goes up, that inverse relationship. And levels above 7.45 represent a state of alkalosis, which is a low hydrogen ion. Remember, pH goes up, hydrogen ion down. The normals in the body, again, are a very tight range. So if we get much below 6.9 pH or above 7.8, that's usually fatal. So the body tries to maintain plasma pH in that very narrow range, 7.35 to 7.45. Start remembering that, because when we interpret our acid base values or the arterial blood gases, that's one of our levels or norms that we need to know. So the body does this keeping in the pH in a normal range in 3 different ways. It's got chemical buffers, it's got the kidneys, and it's got the lungs that can actually help keep that pH normal. Just going to do a little bit of chemistry here to kind of remind you a little about acids and bases. Acids are substances that easily release hydrogen ions when they're dissolved in water. If it's a strong acid, it releases everything when dissolved in water, and that's called dissociation. Weak acids only partially dissociates or releases that hydrogen ion. And again, the strong or weakness of an acidity or the acidity of a solution depends on how much it will dissociate. Bases, on the other hand, are substances that bind the free hydrogen ions in solution. They accept those hydrogen ions, and they have a lower quantity of, or they lower, the quantity of free hydrogen ions in the solution. Strong bases bind them up easily and quickly. Weak bases, not so much. They don't bind very readily or very quickly. So the most common acid in the body is carbonic acid, H2CO3. Most common base is the bicarbonate, HCO3 with a negative charge. The body keeps a pretty constant ratio of acid to base, so the carbonic acid to the bicarb. Usually keeps one acid, or for every one acid there are 20 bases, okay? So for every one molecule of carbonic acid there are 20 molecules of bicarbonate ions. How do we get acids? How are they created? Well, sometimes we take them in with what we eat, but most often our own metabolism is what produces the acids in the body. So when we break down glucose or fatty acids or amino acids, we end up with acids as a result. Basically, carbohydrate metabolism forms carbon dioxide, which basically can be used to form carbonic acid when it's combined with water. Conversely, it will also break down into, carbonic acid will break down into water and carbon dioxide in that kind of chemical equation that moves to one side or the other of the equation depending on what is in more quantity. Proteins, when they're broken down, they form sulfuric acid, and fatty breakdown forms fatty acids and keto acids. And when we don't completely break down glucose, which happens when we're in an anaerobic situation, there's no oxygen, and so we can't aerobically metabolize glucose, we anaerobically metabolize it, that will form lactic acid. So pretty much acids are the result of our own metabolism in our bodies. So our metabolic processes produce all of that excess acid just by normal body function. So the body tends to keep a large amount of base or alkalotic types chemicals around to balance that extracellular fluid and keep the body in that slightly basic range. Remember, 735 to 745. Less than 1% of any of the acid produced is excreted by the kidneys. Usually there is a greater acid control by the buffering agents that I talked about earlier, and also there's greater acid control with respiratory effort. Okay, breathing kind of lowers that carbon dioxide, which in turn lowers the ability for the body to make carbonic acid. Okay, renal shutdown can be present for hours or days before you notice life-threatening acid-base imbalances. But on the other hand, if you have cessation of breathing or stop breathing, you'll have critical acid-base changes within minutes. Okay, so kidney failure won't impact it as quickly as stopping of breathing. So respiratory effort is quite a big part of acid-base balance. Bicarb, on the other hand, the alkaline areas, it's considered a weak base. It's the main buffer of the extracellular fluid. We get that either from what we eat through the GI absorption, or it can be produced in the pancreas. Kidneys will also reabsorb it instead of excreting it when it's the byproduct of some of our metabolic efforts. Of course, it's made when carbonic acid is broken down. And again, we keep that bicarbonate at a level 20 times greater than carbonic acid. Remember again, body tries to keep that plasma pH in the narrow range of 735 to 745 through the three ways I mentioned earlier: chemical buffers, the kidneys, or the lungs. Okay, so let's first talk about the buffers. They are very critical in keeping the body fluid at normal levels. They are always trying to bring fluid as close as possible to the normal pH level. They neutralize or bring acid-base balance as close to the neutral as possible. That way we prevent major changes in the extracellular fluid by either releasing or accepting that hydrogen ion. So the buffers either release or accept that hydrogen ion. They can bind to it. Major chemical buffers are found in the blood, but they're also in the intracellular and extracellular fluid. Basically, they're in all tissues of the body, even the bone. They pretty much act like sponges. They'll soak up the hydrogen ion when there are too many present and things are too acidic, and they squeeze out the hydrogen ion when there's too few present or the system is more alkalotic. They're considered the first line of defense against changes in the free hydrogen levels. They're always present, they act quickly, they can reduce or raise the amount of hydrogen ion and return those levels to normal. They're composed of either chemicals in the body or proteins. And here's some examples of the body's chemical buffers. There's three individual buffers. There's the bicarbonate, we've heard a lot about that, found in both extracellular and intercellular fluid. There's phosphate buffers. Those are actually more in the intercellular fluid. And then there's plasma proteins that are probably the most common. They're all over. They're extracellular and intracellular, consisting of albumin and globulins extracellularly, and hemoglobin intracellularly. Again, those are the things that can bind with the hydrogen ion like a sponge, kind of soak it up or squeeze it out depending on what the body needs. Here's a visual of that showing you the buffer systems in the body intercellularly and extracellularly and how they might address the extra or excess hydrogen ion. Okay, so here's that chemistry I was talking about before, the carbonic anhydrase equation that we use basically to explain how the bicarbonate works, okay? So remember, the hydrogen ion and carbon dioxide are directly related. If you increase one, it will cause an equal increase in the other, okay? So carbonic anhydrase is an enzyme that is used to convert carbon dioxide to carbonic acid and bicarbonate ions, and it can also work to convert the bicarbonate back to carbon dioxide, which can be breathed out. Okay, here's the overall equation, which starting on this left hand side here, the HCO3 plus hydrogen ion, and the double-faced arrow means the equation can go either way. That combining those two items will form the H2CO3, which can also then break down into hydrogen ion and bicarbonate. Simple chemistry. There it is again at the top of this slide. So basically, carbon dioxide gas will form carbonic acid when it is combined with water, as long as we have that carbonic anhydrase enzyme present there. So carbon dioxide is actually a part of that carbonic acid. Carbonic acid, on the other hand, is not very stable, and so it will separate very easily if it's formed from water and carbon dioxide. And again, depending on, looking at the above equation, depending on which side has more, depends on which way the equation will go in chemistry. So there's obviously a relationship between carbon dioxide and the hydrogen ion. So it's directly related. So whenever carbon dioxide increases in the body, more free hydrogen ions are created. And likewise, whenever there is lesser free hydrogen ion production, there is less carbon dioxide, or more produced when one or the other is produced in excess, the other one is too. Okay? So obviously there's a relationship between the pH and the carbon dioxide, because when a condition will cause the hydrogen ion concentration to increase and the pH goes down, there's also extra carbon dioxide. So extra carbon dioxide can be eliminated when we exhale. That will decrease the hydrogen ion concentration. But the net takeaway from this is that when there is a change in the CO2, the pH will change in the inverse or opposite direction. So carbon dioxide, hydrogen, and pH have inverse relationships. Okay? Looking at the relationship between the bicarb and the hydrogen ion, an increase in the bicarbonate will cause hydrogen ion to decrease, and things will become more alkaline. The pH will increase. So the bicarbonate will actually bind with any of the extra hydrogen ion that is floating around and cause that to be more or less deactivated. As we said earlier in the lesson, the bicarb or the base tends to bind with hydrogen ion. So an increase in carbon dioxide level causes the hydrogen to increase and the pH to decrease or become more acidic. The kidneys actually control the bicarbonate level, which can then be released to control that extra hydrogen ion. And the lungs control the carbon dioxide levels, which if we blow that away and lower its level, we will decrease the hydrogen ion that is present. So that's chemically how the lungs and the kidneys are considered our physiologic buffers, okay? So in those chemical buffers, the proteins alone are not sufficient. Respiratory is considered the second line of defense, blowing the carbon dioxide off or holding it in depending on the state of the body, acidic or alkalytic. And the kidneys are the final line of defense, controlling whether or not the bicarbonate is secreted or retained in the blood. Again, remember the phases of defense. We've got the buffers, the lungs, and the kidneys, kind of the three major body defenses against changes in the hydrogen ion. And there are phases of defense. The buffers are immediate. They immediately bind to that hydrogen ion, and the bicarbonate is the major buffer. Compensation is kind of the next phase, can be renal or respiratory. Either of those systems try to compensate. The respiratory is able to do it quite quickly, within minutes. Renal takes a little longer, maybe days, to return the pH to normal. And correction, the final phase, is when things are back to normal and there's a resolution of the primary disturbance or whatever caused the problem to begin with. So again, the initial phase, buffering. Remember, the bicarb is the main buffering system that we have and use. First line of defense against changes in that hydrogen ion level. Bicarb, phosphate, and proteins are what mainly act as the buffers. They're everywhere. They're present in all the fluids, so they have pretty fast action. Secondary phase is going to be the respiratory system. When those chemical buffers are not sufficient, the respiratory system will alter the rate and depth of ventilation and thus either hold in or blow out the carbon dioxide, which then also controls the amount of free hydrogen ion. As the level of carbon dioxide goes up or down, the hydrogen ion does the same thing, going up and down to match the changes in the level of carbon dioxide going up and down. Also, there's to remember how respirations in general are controlled. There's neuroregulation of respirations, usually looking at the lower or middle right-hand side of this diagram. There's chemoreceptors scattered throughout the body, and they sense an increased hydrogen level. And when they're stimulated, the rate and depth of respiration are increased, and that will decrease carbon dioxide, decrease the hydrogen level. And that is all controlled by the neural centers in the body that control, basically in the medulla, they control the action of breathing. So lungs are considered to be physiological buffers as they control whether or not that carbon dioxide can be taken in, kept in, or blown off. And that is a compensation for acid-base disturbances in general that are primarily metabolic, like a lactic acidosis when you're exercising. This is all under the control of the medulla oblongata, which is the center that stimulates or commands the lungs to breathe and the respiratory rate to change. Again, the medulla oblongata springs into action, if you will, in response to the amount of carbon dioxide in the extracellular fluid. Respiratory system, therefore, is pretty sensitive to changes in the pH and will begin changes in the rate and depth of respiration within seconds to minutes of those chemoreceptors sensing the high level of hydrogen ion in the blood. Remember that there are age-related issues also with the elderly. They have a reduced amount of gas exchange, and so they have more problems getting rid of that carbon dioxide. And so when they tend to have an increase from a disease process of hydrogen ion, they have more problems with their respiratory system jumping into action and helping them to compensate. So the final phase of compensation, it's a correction of the original imbalance, again, like I was saying, can take days or longer before the body will return to homeostasis. In general, that is considered to be a resolution of the primary disturbance. So the renal system basically regulates acid-base homeostasis by altering whether or not bicarb is reabsorbed or added back into the blood, whether it can create new bicarbonate, which it can through basically putting together water and carbon dioxide, but it takes care of the excess hydrogen ion so that's not creating more acid. Or it can actually secrete bicarbonate to get rid of it. It can secrete it into the urine and then possibly keeping that hydrogen ion. If the body would be in an alkalotic state, the kidneys will actually address it by getting rid of that extra bicarbonate and retaining the hydrogen ion. Okay, it's a stronger, more permanent response, but it takes longer. And again, the kidneys in general will move to correct that initial imbalance. Okay, so here's just a little more chemistry again, showing you how the renal system will actually regulate acid-base balance by either reabsorbing or generating new bicarbonate ions, and it can either gain or lose hydrogen ion. So there we have our equation again, with the carbon dioxide water on one side can go back and forth to carbonic acid, or it can dissociate into the bicarb and the hydrogen ion. If we lose the bicarb, it's the same as gaining extra hydrogen ion, and reabsorbing the bicarb is the same as losing that hydrogen ion, because the equation will shift one way or the other to the side with the more quantity. Kind of that's Cliff Note version of chemistry, but gives you the idea. Kidneys control that metabolic buffer, sodium bicarb, by excreting acidic urine or alkaline urine. So that's another place that the bicarb can be obtained. That also works within several hours to days, very effective, again leading to reabsorption of the bicarb, or can secrete and reabsorb those hydrogen ions depending on the acid-base condition of the body and what is needed. So just a few things, remember, and the lungs will adjust their ventilatory response to carbon dioxide, and they compensate for metabolic disturbances, either conserving or retaining carbon dioxide. Acute rises in the carbon dioxide is obviously a very powerful stimulant to cause somebody to breathe or ventilate or have respirations. So normally the decreased oxygen level won't stimulate ventilation significantly until it falls very low. And the one exception to this is somebody who has COPD or emphysema and their body no longer responds to the carbon dioxide, but instead responds to oxygen levels. And you'll probably hear more about that as you guys get into more of the respiratory system. Additional notes about the kidneys. Again, they regenerate the bicarb ion and can reabsorb them into the renal tubes when respiratory acidosis is present, and some of the metabolic acidosis. The kidneys will try to get rid of that hydrogen ion and conserve the bicarb. In the presence of alkalosis, the kidneys will save the hydrogen ion and excrete the bicarb. Again, renal compensation is slow, taking hours to days. Some of the ways that the kidneys can actually remove that hydrogen ion is to actually, when the body's breaking down proteins, ammonia is formed, and ammonia can be secreted in the urine and combined to that extra hydrogen ion, and thus pull that out of the system and then free up that bicarbonate. Okay, so ammonia can be formed in the kidneys and get rid of that extra hydrogen. Again, the responses, the first responders are the chemical protein buffers, second is the respiratory, and third is the kidneys. Here just a little memory aid on acid-base balance. When there's too many hydrogen ions, there's more acid. The body tends to keep in a very narrow range and will do different things response-wise to get the pH back where it belongs. We see number 1, Buffy buffer, and number 2, respiratory, number 3, the renal systems. And there are some normal pHs by body fluid in the lower right-hand side. You can see gastric, very acidic, urine, slightly acidic, arterial blood, basic, venous blood, a little less basic, Cerebral spinal fluid tends to be a little tiny bit basic, and pancreatic fluid basic also. Okay, let's talk a little bit more about compensation. Been saying that off and on. So both the kidneys and the lungs can compensate for imbalances. Usually the respiratory system will correct for imbalances from metabolic problems. So when the lungs are able to fully compensate, pH returns to normal. And the same with the kidneys. When the kidneys make adjustments for imbalances that are caused by respiratory systems, we say that the kidneys are compensating. Again, things are fully compensated when the pH returns to normal. There is partial compensation going on because we see in those particular levels of arterial blood gases that we will be examining, the buffers are in the process of working, or the respiratory or renal system is in the process of working, but it isn't completely resolved. The problem hasn't been completely resolved, so that is called partial compensation. And when things are getting worse and worse and worse, it's called decompensation, a worsening state of acid-base balance. In partial compensation, the respiratory or renal system exerts specific actions to correct the pH but can't fully return things to normal. That's partial compensation. Still considered good because, we're kind of preventing the situation from worsening or becoming life-threatening or severe. So partial compensation is good because it means we're heading in the direction of full compensation. Talking a little bit now about acidosis, the state of acidosis in the body. It's considered that the acid-base balance has been upset because there's an excess of hydrogen ions. The pH is less than 7.35. The amount or strength of the acids is greater than normal compared to the bases, and it's usually caused by some kind of a disorder or pathologic process. It can be a metabolic acidosis or a respiratory acidosis, or it could be both. We'll see in a little bit here. So acidosis is a problem where there's either too much acid, too much hydrogen ion, or not enough base floating around to take care of the hydrogen ion. Alkalosis, on the other hand, the acid-base balance is upset because there's an excess of bases. Usually it is the bicarbonate ion, or there can be a decrease in the free hydrogen ion level. Regardless of the cause, the pH is now going to be greater than 7.45. Again, it's a manifestation of a problem, and it can be caused by metabolic or respiratory problems or both. Okay, so it's either a problem where there's too much base, too much bicarb, or not enough acid, not enough hydrogen ion. Okay, and that's all we have for this set. Thank you.